Okay guys, so this is Kc for Zen Masters or Kc in equilibrium. This is, I think, quite hard. It's certainly more difficult than all the other case stuff, which we do, I think anyway. So basically, imagine I've got a dynamic equilibrium set up, and I've got a mole of A, which is gas, goes to a mole of B, which is also a gas. And my delta H is minus 155 kilojoules per mole. This delta H, by the way, always talks about your forward reaction, so going from left to right, if you're facing this way. So just remember that, delta H, always your forward reaction. They'll usually always tell you this. And all we're going to talk about is what effect temperature and concentration, a change in temperature and a change in concentration, will have on the position of equilibrium, the concentration of your products, and therefore the Kc. Okay? Throughout this, the most important thing to remember is Le Chatelier's principle, which is if a closed system is in dynamic equilibrium and it's subjected to a change, the position of equilibrium will shift to minimize that change. What that basically means is if you try and change something, the position of equilibrium will try and stop you. It'll try and reverse what you've done. So imagine it's like a really nasty guy. If you increase the temperature, the position of equilibrium will try and bring it back down again. If I was to decrease the concentration of something, the position of equilibrium would bring it back, or try and bring it back up again as much as possible. So always try to do the opposite of what you've tried to do or what you've changed about it. Okay? So before we do anything else, let's set up our Kc expression for this. Kc is just products over reactants, so it's going to be B over A, like that. And to start off, let's do what an increase in temperature would do. So increase the temp. If they ask you a question like this, the first and the most important thing to remember, apart from Le Chatelier's principle, is this delta H at the top here. This tells you which of your reactions is exothermic and which is endothermic. So the fact that this delta H is negative means your chemicals have lost energy, they've given energy out. Energy has exited, so it's exothermic. So my forward reaction, remember delta H always talks about your forward, must be exothermic, which means your backwards must be endothermic. So that's the first step. We've set up which way's exo and which way's endo. We won't be able to do the rest unless we know that. So let's think about this. Position of equilibrium is essentially a ratio of your forwards rate of reaction compared to your backwards rate. And I always imagine it as just an imaginary line on your reversible reaction sign. If your forwards rate exactly equals your backwards rate, and we have a dynamic equilibrium, I imagine that, and you can just use in the exam, actually, use your hand or a finger or a pen or whatever, as being right in the middle of this reversible reaction sign. That's if your forwards rate equals your backwards. If I was to make my forwards rate greater than the backwards, so we're getting more of B made, I always imagine that, the position of equilibrium has shifted to the right, so I imagine that as this line shifting to the right-hand side. And that means your forwards rate is more powerful than your backwards, more faster. If I was to shift the position of equilibrium to the left, that means my backwards rate is faster, so I'm going to produce more of A, and I'm going to start using up B. So A would increase and B would decrease in concentration. Okay, so position of equilibrium, this imaginary line which tells us which rate is faster. So let's have a look what would happen to this position of equilibrium if I increase the temperature. Well, exothermic reactions are things like a fire or an explosion. What do they do to the temperature of the surroundings? Well, they increase them, don't they? You wouldn't cool your hands on a fire. And endothermic reactions, they suck in the heat, so they make the surroundings cooler. So I've increased the temperature. Le Chatelier's principle says that the position of equilibrium will try and bring it back down again. How would the position of equilibrium shift to bring it back down? Well, it would shift to make more endothermic reaction. So if I was to increase the temperature, my position of equilibrium would shift to the left in the direction of the endothermic reaction. And it's important to include that as well, why it's shifting, because this is the direction of the endothermic reaction. So for our first of 3 bullet points, what would happen to the position of equilibrium? Don't abbreviate it like this in the exam. Position of equilibrium would shift to the left-hand side. if you're facing the board like this. What will this do to the concentration of my products? Well, if I've got more backward reaction, the concentration of my products would decrease, get lower. And again, don't write it like that in the exam. I'm being morbidly lazy, as I always am. And I guess the ultimate question is, what will this do to Kc? So let's go back to this Kc expression. Kc is a ratio of your product's concentration over your reactants. But we've just said by increasing the temperature, my concentration of B will decrease and A would have increased. So what's that going to do to this number here? Well, if I'm making this number smaller and this number higher, that's going to make the answer a lot smaller. So basically what was going to happen to Kc is Kc is also going to decrease. And there's actually an easy way to remember this. If ever your position of equilibrium shifts to the left, you're going to be making less products. So your Kc is going to be lower. Because remember, Kc is a ratio of products over reactants. If ever your position of equilibrium shifts to the right-hand side, then Kc is going to be a bigger number. So a way of thinking about it is the bigger Kc is, the more products you have, the more your position of equilibrium is shifted to the right. Okay? So that's an increase in temperature. Obviously, if I decrease the temperature, the position of equilibrium would try and bring it back up again by shifting to the right-hand side. That would give me more products and therefore make Kc a larger number. Okay? The more bigger Kc is than 1, the more products you have compared to reactants. So the more your position of equilibrium shifts to the right. Okay? So that's temperature. We're also going to talk about concentration as well. Although when I talk about concentration, pressure works in pretty much exactly the same way. Okay? So we've still got our concentrations here, and let's say at dynamic equilibrium, in fact, before I go on about this, there's one extra thing I wanted to say about temperature. Temperature can change Kc. Temperature is powerful enough to completely mess up the dynamic equilibrium and set up a new equilibrium with a different Kc. So really, whenever we quote a Kc, we should also state the temperature. Because if I was to change that temperature, I would also change the Kc. So temperature is rock hard. It kind of reminds me of myself. It's dead hard. It will change Kc. However, let's talk about concentration. Let's imagine I have a concentration of 0.2 moles per decimeter cubed A and 0.4 moles per decimeter cubed B. Popping this into my K, and this is at dynamic equilibrium at a certain temperature, let's say 25 degrees C. So popping this into my Kc expression, that's going to be 0.4 over 0.2, which is going to equal 2. So at 25 degrees C, the Kc, the equilibrium constant for this reaction is 2. Okay? At that temperature, this Kc will always be 2. Okay? This is the most important thing to remember. You've got to get this. Kc is boss. Apart from temperature, Kc is boss. It controls the concentration and the pressure. So because the Kc is now 2, we are in dynamic equilibrium. If I put my concentrations into this equation at 25 degrees C, and the answer comes out as anything else but 2, then it's not actually the Kc, because we're not in dynamic equilibrium. And that's a really hard fact to kind of get your head around. Okay? Kc controls concentration, not the opposite way around. If I was to change these concentrations, Kc wouldn't change to fit it. The concentrations would change back until they fit Kc. And we wouldn't be in dynamic equilibrium until they do equal this number, providing we keep the temperature the same. So let's have a look. Let's say I change this number here to 0.5 moles. So I increase the concentration of B. What's that going to do? Well, sticking these numbers into my Kc expression, I'm going to have 0.5 over 0.2. Notice how I've not said Kc equals this, because it doesn't. We're no longer in dynamic equilibrium, so we don't have Kc. You can only have Kc when you're in dynamic equilibrium. And if I change one of the concentrations, I've completely messed up the equilibrium. So popping that into my calculator, I will get 2.5. This number is not 2. That's proof that I don't have dynamic equilibrium. How am I going to make this number go back to 2? Well, the concentrations are going to change. So basically, my 0.5 is going to need to go down, and my 0.2 is going to need to go up. And another way of saying that is, well, if you want B to go down and A to increase, what have you got to do to the position of equilibrium? You're going to shift it to the left, haven't you? So if I was to increase the concentration of B, the position of equilibrium would shift to the left. This number would decrease, B would decrease, A would increase until we reached a concentration or a set of concentrations which equal 2 again. And the second these concentrations reached a ratio which equaled 2, then your position of equilibrium would stop, your concentrations would remain the same, and we would have Kc again. We would be at equilibrium. Okay, so temperature can control Kc, but pressure and concentration cannot. They are not changed by in any way. Sorry, they do not change it in any way. And also catalysts, they won't change Kc either, because a catalyst increases your rate of reaction, but it increases the forwards rate by exactly the same as the backwards rate. So imagine I double my forwards and I double my backwards. What's that going to do to the position of equilibrium? Well, it's just going to end up in exactly the same place, isn't it? Because you just doubled both things. So that wouldn't change Kc. Remember, the further towards the right we go, the larger Kc is. If I stay the same, then I haven't changed Kc. Okay? So most important thing, pressure and concentration do not change Kc. They will change themselves until they hit Kc. But temperature can change it.